today we'll be looking at optical activity. Optical activity is also, we are still in isomerism, okay, under stereoisomerism. But I want to talk about optical activity before we go to enantiomers, okay? So now, optical activity. When do we say a molecule is optically active? That's the question I want to ask. When do we say a molecule is optically active? Now, a molecule is said to be optically active when that molecule has the ability to rotate a plane polarized light. Now, when we say a plane polarized light is simply a light that travels in one direction. Okay? So if you place a molecule in front of a plane polarized light and the molecule rotates the light clockwise or anti-clockwise, then the molecule is said to be optically active. So this optical activity is what we use to determine if a compound is optically active or optically inactive. Now, for optically active compounds, they can rotate a plane polarized light either clockwise or anti-clockwise. Now, in this case of study, that clockwise movement or anti-clockwise movement will represent it as what? Dextro-rotatory movement or levo-rotatory movement. Okay? We'll talk about those movements as dextro-rotatory or levo-rotatory movement. Okay, so such movements can be also, we use a plus sign to illustrate dextro and a negative sign to illustrate what? A negative sign. Now, for you to be able to rotate a plane polarized light, it means you're optically active. And optically active molecules have what we call a chiral center. They have what we call a chiral center or a chiral carbon. Now, what is a chiral center? A chiral center or a chiral carbon is a carbon whose four attachments are totally different. They are not the same. They are not the same. Okay? Example is lactic acid. Lactic acid is called the IUPAC name for lactic acid. Okay? The IUPAC name for lactic acid is 2-hydroxypropanoic acid. Propanoic, acid. Now, how do we draw the structure of this compound? Look at this compound. We have C, double bond O. This is OH. Then 2-hydroxy. Let's put the OH here. Let's put H here. Then we have this. Now, why is this compound said to be optically active? It is said to be optically active because it has a chiral center. Where is the chiral center? Not this one. This carbon here is not chiral. I hope you know. This carbon here has 1, 2, 3, 4. Look at the 4 attachments of this carbon. I have 3 hydrogens. For the fact I have the same thing connecting to this carbon is not chiral. But look at the carbon in the center here. This carbon has 1, which is this group here, 2, which is this group here, 3, which is this group here, and 4, which is everything here. So this carbon at the center, is said to be chiral. This carbon here is not chiral. You know why? Once you see a double bond bonded to a carbon, that carbon is not chiral, because for you to be chiral, you must have 4 different attachments surrounding it. But this carbon here has only one, this carbon here has only 1, 2, and 3. So it doesn't have up to 4. So because this carbon is not completely having 4 different things that are the same, then we say that this carbon. So the only chiral carbon here is the central carbon here. So we can say that 2-hydroxypropanoic acid, otherwise called lactic acid, is optically active. And now, you must not just have a chiral center for you to be optically active. You must have a chiral center and also must not have a plane of symmetry. Now, a plane of symmetry is a line that divides a molecule into 2 different halves. There is no plane of symmetry in this molecule. No matter how you cut this molecule, you can't get the same thing at both sides. Okay? So, molecules that have a chiral center and do not have a plane of symmetry are said to be what? Optically what? Active. So what it means is that for you to be optically active, you must not have a plane of symmetry, and you must have a chiral center. So for the criteria for optical activity is 1, chiral center, and 2, the molecule must be what? Asymmetric. Okay? So now, a good example of an optically active compound is what we call enantiomer. An example of an optically active compound is what we call enantiomer. Enantiomers are mirror images. Enantiomers are molecules that have mirror images and are non-superimposable. That is, if you look at the molecule in a mirror, the molecule in that mirror cannot go into the molecule. Why? Because the parts are in different sides. Just picture yourself in the mirror. Imagine your image in the mirror. That image, if it's to come and superimpose, that is, enter inside you, it cannot penetrate because the body parts are not in the right direction. So you have to rotate it so you can be able to superimpose. So enantiomers are mirror images that cannot superimpose, that cannot be joined together like that without rotating it. So now, I will not go into details, okay? I will just explain to you enantiomers. A good example of enantiomers are, you can see enantiomers in 2-hydroxypropanoic acid, okay? This molecule you are seeing here, if you look at this in the mirror, it is going to look the other way around. So the mirror image of this molecule is what we call enantiomers. And these enantiomers can either have a dextro-rotatory movement or a levo-rotatory movement. So enantiomers are mirror images that are non-superimposable. And now, when you mix 2 enantiomers together, you will now form a mixture. If you successfully mix 2 enantiomers together, you will now form a mixture which we call a racemic mixture. So a racemic mixture is a mixture of 2 equimolar quantities of enantiomers. And this racemic mixture is optically inactive. This racemic mixture is optically inactive because they will cancel out. Their optical activity will cancel out because we are joining 2 enantiomers together. And once they come together, those optical activity will cancel out. Okay? So, and you can actually separate this mixture through a process we call resolution. Okay? So we can use a process called resolution to separate these 2 mixtures if we want to separate them to their various enantiomers. So enantiomers are mirror images of each other that are non-superimposable. So take note of that. So I will not go into detail because this outline does not require for us to go into detail to look at. We would have represented the enantiomers using Fisher projection and the perspective formula for you to understand the configuration and the rest of them. But due to the limit of this study, we are only going to talk about just brief aspect of it. Just know what is enantiomer. Know that enantiomers arises as a result of optical activity, and they have chiral centers, and they do not have a plane of symmetry. Instead, those compounds that have chiral centers with plane of symmetry, we call them mesocompounds. They are called mesocompounds. But I won't talk about it because in the scope of this study, we are not expected to know what is mesocompound. So mesocompounds are those compounds that have 2 or more chiral center, but with a plane of what? Symmetry. Okay? But enantiomers have a chiral center, but they don't have planes of what? Symmetry. So, and they are optically active. And take note, these mesocompounds are optically inactive. They are optically inactive. Okay? So they are not active, just like they can rotate a plane polarized light. Okay? So molecules that can rotate a plane polarized light are said to be what? Optically active. So in enantiomers, the isomers of enantiomers are the ones with the dextro-rotatory, and the ones that can rotate clockwise, and the ones that can rotate what? Anti-clockwise. Okay? So I won't really talk much. So this is all we have to talk about under stereo. So I believe that your outline does not require more than this explanation I've given to you. So just know what is chiral center or chiral carbon, know what is enantiomer, know what is racemic mixture, know what is resolution, know what is optical activity and what causes optical activity, and know also what is a plane polarized light, a light that travels in what? In one direction. So the instrument we use to measure this optical activity is what we call the polarimeter. We call it the polarimeter. So take note. So I have listed all the possible points you need to know under this course. The polarimeter, or sometimes the Polaroid, is also called Polaroid. So you can use it to what? Measure this optical activity in molecules. So remember, under stereo, there is no much questions you will see in your exams from here, but focus more on the what? On the constitutional isomerism. But for this part, dwell more on understanding definitions and explanations that I've explained on the board here. I believe with this, you should be able to understand or deal with any question you will see in your exams under stereo isomerism.